I think it's supposed to. Like,
yeah.
Like
but like instantons were translated as instant phones a few times.
could be valuable.
Yeah.
Burn phones.
Right, and especially in a conversation when you switch topic, then it thinks it's still the same topic and it tries to integrate it sometimes. I mean, you can definitely reconstruct what the meeting was about. So it's actually kind of helpful. Emails it to you, yeah, we should do it for faculty meetings, actually.
We don't need
no need a secretary. And it could be equally hilarious, just by mistranscription.
Part of it, like.
Yeah.
An option to feed in some AI. Load the mics notes and just prepare this time.
Yeah, sure.
Ready to start whenever you are? You good?
Yes.
Yeah. Excellent. All right, we're very happy today to have Claudio Andrea Manzari here. Claudio got his PhD at University of Zurich, and then he moved over to Berkeley for his postdoc starting last year. And he's going to be here today to tell us about some non-axion solutions to the strong CP problem. So without further ado, Claudio.
Thanks a lot, David, for the introduction. It's really a pleasure to be here. So today I would like to tell you about a research line that I recently entertained, and I believe can bring some very interesting and better understanding of one of the probably arguably most robust problem of particle physics, which is the strong CP problem. So
Click. You click and then
click on,
and then now
good.
You should be able to use your
arrows. Okay. Sorry. So this is the outline of the talk. I will start reminding ourselves a little bit what is the strong CP problem, and then I'll move to some of the solutions that have been proposed in the literature, focusing on two of them: a solution based on parity and solution based on CP as exact symmetry of nature. For each of these two categories, I'll discuss one novel mechanism that I worked out with some of my colleagues. The first one with Quentin, Lawrence, and Christiane, and the second one, which is still a work in progress, with Lawrence and B. So, first of all, let me remind you that QCD with n flavor has a large global symmetry in the limit where we take all quark masses to 0. So we expect some UN vectorial times UN axial. But actually, experimentally, we measure only the mass of the up and the down quark to be much smaller than lambda QCD. Therefore, we at least expect to see in nature some sort of U2 vectorial times U2 axial symmetry. Now, the U2 vectorial, in fact, is what we observe in the iron multiplets. It can be easily decomposed in an SU2 of isospin times U1 baryon number. While we don't see a U2 axial, and we expect to not see it because we know that it is spontaneously broken by quark condensate of the form QQ1. So since it is spontaneously broken, we also expect to see 4 Nambu-Goldstone bosons, which are associated to its generator. However, experimentally again, we only see 3 light Goldstones, pi 0, pi plus, and pi minus, while the 4th lightest meson, the eta meson, is much heavier than the pion. So at the time of these observations, this problem was dubbed the U1A problem by Weinberg and other people. And this one soon after solved by Toft, who showed that the U1A part of the U2A is in fact anomalous with QCD and therefore is not an exact symmetry of QCD. So this means that the associated current to the U1A is not conserved, and that the chiral rotation on quark fields shift the axion by a quantity proportional to this integral, and therefore x of GG dual. Now, at first sight, GG dual looks like a total derivative, so we may wonder if this integral in fact goes to 0. talk showed that this is not the case, and there are gauge configurations for which the shift of the axion is non-zero due to the complicated nature of the QCD vacuum. So as a result, U1A is not a symmetry of QCD, so the U1A problem was solved. But this effectively added to the QCD Lagrangian a new term, which is P violating, T violating, and C conserving, therefore also CP violating. It looks like this: some dimensionless coefficient in front of the operator GG dual. And this parameter theta is a free parameter in principle of the theory. And this measures how badly is P and CP violated in the strong interaction, being this the only operator which violates P and CP in the strong interactions. So this is not the end of the story. The story is made a bit more complicated by considering also weak interactions, since theta is also shifted by the chiral transformation on the quark fields needed to diagonalize the quark mass matrices, such that in the end what we get is an operator GG dual with a Wilson coefficient proportional to what I use from now on theta bar, made of two components: a bare theta angle plus the argument, the determinant of the Yukawa up and down matrices. Now, first of all, note that these two terms, at least in the standard model, are not related one to the other. Therefore, there is no reason why they should cancel. So we can then ask ourselves, how do we measure theta bar? There are a few observable where theta bar, this parameter theta bar shows up. The most relevant one is the Newton EDM, because this gives the strongest bounds on theta, and the bounds is order 10 to the minus 9. So, yes, I also always like to show the slides where one can see the improvement on the measurement of the Newton EDM over time. You see that there was quite a good improvement from the 50s to today. And in the next few years, we expect a further improvement by 2-3 orders of magnitude, which looks very promising in terms of testing theoretical prediction for this parameter. Okay, so the strong CP problem is the lack of understanding of why theta bar is so small, why this parameter is so small. And at the beginning I said this is probably one of the most robust problems of the standard model for the following reason. First of all, this parameter being small is not natural nor technically natural, in the sense that we don't see any enhanced symmetry in the limit where it goes to 0. There is almost no anthropic solution. It is true that theta bar order 1 would mess up the relation between neutron and proton masses, but its effect very quickly decouples when it becomes smaller than 0.1, 0.01. Then the standard model has another CP phase, which is the phase of the CKM matrix, which is pretty big, it's order 1. And finally, any kind of UV completion of the standard model you can think of usually introduces new phases to the theory, and these phases would generate theta bar at some loop level, making its expectation value large, at least compared to the current bound of 10 to the minus 9. So, in my opinion, the strong CP problem is also very interesting because it is hard to model build a solution to it. And this is the reason why in the literature we actually have few classes of solutions. The simplest one is undoubtedly a massless quark. If we had a massless quark, we would have an additional global chiral U1 symmetry, which allow us to rotate one of the quark fields, make a chiral rotation of one of the quark fields, making theta bar unphysical, since we can just rotate it away.
In what sense is the solution? Because then when you explain why it's massless and there's no enhanced symmetry, like either.
So sorry, say again. This is a solution just because it's an unphysical parameter of your theory.
Yeah, but then you need to explain why the quark is massless.
Is there Carl symmetry?
No, because for one, it's anomalous also. If one quark is massless, there is no enhanced symmetry. So it looks like you exchange one parameter for another.
But if one quark is massless, you have a U1 in additional U1.
It's anomalous.
With single quark, there is an anomaly.
Yeah, that's right.
The same anomaly.
We never told this.
Is it technically natural? So does it stay?
No, because
No, because it's saying it's not an exact symmetry of the
There is
theory,
no
it's just a
symmetry.
normal.
so it's even
Yeah,
hard to
okay,
say what
okay.
does it mean for quark.
Yeah, honestly, I'm not familiar with the
Doesn't the eta essentially become the axion then? I thought that something like it's anomalous, so it gets a potential, but I thought that the minimum of the eta can shift essentially to cancel this off. I thought it was one way.
I'm not arguing that there is no CP. That would explain that there is no predict that there is no CP. But why this is 0? Actually, it's even very tricky to say what does it mean for M quark, because when you say M up mass, which mass we're talking about? It's presumably some UV.
yeah, of course.
But it's very hard.
Yes.
It's not definable in terms of some
So
symmetry,
I'm
right?
not familiar with this construction. I actually don't know if people came out with some with fixing this problem with some solution to this. I don't know, because in any case, I would argue that this is out of favor because of lattice results and so. Okay, so moving on, we have probably the most well-studied solution, which is the axion solution. So here the idea is very simple. We have a global chiral U1 symmetry which mimics the U1A, so as to be anomalous with QCD. Then we want to spontaneously break it in order to have a Goldstone whose BEV, you can see here from minimizing this potential, is theta bar FA and dynamically drives the coefficient in front of the operator Gigi dual to 0. And finally, there is a class of solution on which I focus today, which are based on the idea that parity or CP may be exact symmetries of nature. Now, if you just saying that, set the theta bar parameter to 0, because we cannot write in our Lagrangian any Gigi dual operator, because this is P and CP violating. And from a classical point of view, it is really nice to see how this works. Imagine to have a neutron with some spin and EDM, which are aligned. Now do a parity transformation. The spin is left invariant. The EDM changes sign, so changes direction. You end up with a particle which has spin and EDM anti-parallel. Experimentally, we see only one neutron with spin 1/2. So the only solution to this is that mu has to be 0. Similarly for CP, where the spin is left invariant and mu changes. Okay, but this is only from a classical point of view. Now, it is clear that this cannot be the end of the story in the sense that P or CP cannot be exact symmetries of nature at arbitrary energy scales. The reason is that we see the standard model to violate badly both P and CP. So we need to break them. And one may be worried that now the breaking of the symmetry may reintroduce somehow the parameter theta bar. So let's assume the following. Let's assume that at some high energy scale we break our UV compression of the standard model, we recover the full standard model. From this scale on, parity and CP are broken, and we only have the standard model. And we may want to compute the corrections to theta bar induced by this. It is easy to see that the like one loop diagram. So first of all, in the standard model, corrections to theta bar come from corrections to the quark hours. It's easy to see that one loop you cannot pick any phase clearly because this diagram goes as Bij star, where B is the CKM matrix, and given the unitarity of the CKM matrix, this diagram is real. Then you can go to two loops. Here it is harder to see that you cannot pick any phase. We would expect the opposite since you have 4 CKM insertion, and you may think that you may pick up the just-log invariant, which is a phase-independent measure of CP violation in CKM. However, Ellis and Gaillard showed that all these diagrams sum to 0, and that the only first non-finite imaginary contribution comes at 3 loop. So at loop you have a correction to theta bar in the standard model, while divergent contribution, and therefore RG running of theta bar, is only induced above 7 loops. So they estimated the correction of theta bar at 3 loop in the standard model, and you see that the result is extremely small, and in particular compared to current value. So we can safely neglect this contribution. In general, whatever is your UV completion, one should check this, but at least in the standard model, it is reassuring the fact that this is extremely small. And so even if we solve the strong CP problem in the UV, this means that this solution will remain intact in the IR. Okay, so now let's move to a parity solution to the strong CP problem. And what is the main idea here? Again, theta bar is made of two components. You have a bare theta angle, and this has to be zero if parity is an exact symmetry of your theory, just because GG dual is sent into minus GG dual by parity transformation, and therefore theta has to be zero. And then you have the contribution from the weak interactions that goes as arc depth of YULD. Now, as we'll see in a second, in general, parity enforces your Yukawas to be Hermitian. The determinant of an Hermitian matrix is real, and therefore arc depth over ULD is zero. And note that Yukawas can be complex, which means that at least we won't necessarily have problems with the phase in the CKM matrix. We can at the same time recover the phase in the CKM matrix and still keeping theta bar to be zero. So what is the simplest realization of this idea? Well, so if you want to think at some sort of UV completion for standard model, one has to generalize its definition of parity. Usually is the usual definition of parity composed with the Z2 symmetry. Z2 symmetry that in the simplest case exchanges two gauge groups, in this case SU to left, SU to right. The right-handed quarks are embedded in doublets under SU to right, and you need an additional Higgs to break your starting gauge group, SU3, QCD, plus SU to left, plus SU to right, plus SU1, D minus N, to the standard model. Now, although this kind of model looks really minimal and simple, you soon realize that you start having problem, for instance, with the Yukawas. Yukawas here are only allowed at dimension 5, so you have to come up with additional ingredients to explain how these operators are generated. And so this minimal as a solution to the strong CP problem, but it requires many more ingredients afterwards to recover the full standard model and explain all observable data. The immediately following step is to not only double the SU2 gauge group, but also U1. This model has been proposed firstly by Barr and Senjanovic, then studied by Lawrence, David, Kisuke. And the idea here is that once you double also U1, you necessarily have to double also the fermion spectrum. The reason is that now parity is exchanging fields that are charged under the standard model gauge group with fields that are now charged under some additional group that have nothing to do with the standard model. And so to recover the standard model, you need to double the fermion spectrum. And Yukawas are allowed in both sectors, and they are related by this parity transformation in order to get to keep the arc depth of YUAD 0. Now, I won't delve into the details of this model, but this was the starting point for one of our recent work where we thought, so if you want to think at some sort of real UV completion, like gut UV completion of this model, you may think about some sort of SU5 cross SU5 theory. And the first question that you should ask yourself is, okay, now what happens if I fully mirror the standard model? Now my parity is a Z2, which exchanges the standard model with its own copy, times the usual definition of parity. And the problem here seems the fact that now parity exchanges GG dual with G prime dual, where G prime are the field strength tensor of SU3 in the mirror world. And therefore it's not enforcing theta to be 0 anymore, but it's just setting theta to be equal to some theta prime, which is minus theta. So the two thetas are correlating, anti-correlating in the two worlds, but each of these two sectors have its own anomaly term for GG dual.
So just understand the logic. So just the way that parity invariant model on its own looks good, right? So for CP, for solve this
This-
problem.
this-
Now you're trying to achieve something more, right? Not just
Yeah, okay, first of all, so this model looks good. Yes, some little problem that are, for instance, should explain, so may lead to some cosmological problem given the kinetic mixing you can have between these two phase groups. Okay, you have to make the mirror world very heavy because otherwise you have problems with the light stuff. Like if you have, so these guys are all charged under QCD. So this means that the mirror quarks are also charged under QCD and will form bound state with standard model quarks that will be fractionally charged. So you have to make them very heavy to escape all direct detection bounds.
In your other model, you will totally separate it. So they will also,
At the beginning,
SU3 will talk only with its own SU3.
That's the starting point. Then, okay, I'll go on. You will break that, but the fact that you break only in the IR alleviate a lot of these bounds. Okay, I'll
trying to understand the motivation, what you're trying to achieve there. So this is a proof of principle model, right? But you're not happy with some
There are
cosmological
some
aspects.
details, yes, and then if you want to take some gut UV completion of this, well, at least the first thing I would come to my mind is some sort of SU5. You start from some sort of SU5 cross SU5 model, and then you break down to copies of the standard model. That's what led us to study these alternative solutions.
So by gut UV because SU5 cross SU5 also not. So by gut UV completion, what exactly you mean? You're happy with SU5 cross SU5, but not happy with this. You're not trying to combine everything in a single.
No, that's right. But at least you unify in a most minimal version of this, no? In SU5 cross SU5, you start from 2 couplings. Here you're starting from 1, 2, 3, 4, 5 couplings. So it looks less minimal at least. Okay, so yeah, I was saying the problem is that it looks like parity is not actually solving the strong secret problem here. However, you may realize that if we now break these two SU3, each one has its own anomaly term. If this is broken to the diagonal subgroup and you identify this diagonal subgroup with QCD, then you find that naturally the theta term of the diagonal subgroup is proportional to theta plus theta prime. So, and if these two are anti-correlated now, this is automatically zero. And this is exactly what happens because of parity. That's exactly what parity is doing. Okay, so now this is true for the Bayer angle. What about the contribution from the weak interactions? Well, parity also enforces the Yukawas to be the complex conjugated of the Yukawas in the mirror world, such that when you compute arc depth of this matrix, you get a minus sign from the fact that one is the emission conjugated of the other. And in fact, at the breaking scale of the 2SU3, what happens is that the full theta bar is 0 for QCD. Okay. Now, as we commented before, we need to break parity at some point to recover the standard model. And what does it mean in this kind of models? Breaking parity means that the VEV of the mirror Higgs is much larger than the VEV of the standard model Higgs. There is no conventional way or to do this in the literature, in the sense that people usually have done this just assuming some soft breaking in the scalar potential. Some attempt of UV completing this was done by Lawrence and Keisuke by looking at this Higgs parity, where the two X's belong to a fundamental representation of some SU4 global symmetry. But I'm discussing these details out of the scope of this talk, and I just want to mention what happens when you break parity. In principle, you have to take care of dangerous classical correction from higher dimensional operators. For instance, here you can very simply have operator that goes as h squared plus h prime squared, two opposite coefficients. These are not exchanged by parity, and this gives you a bound on the upper, an upper bound, sorry, on the scale v prime. And then in general, you have quantum corrections. However, this model is just standard model plus its own copy. So any kind of corrections will be exactly identical as the one that we discussed before in the standard model. And will still remain completely negligible with respect to current bounds. So this is everything I wanted to say concerning this mechanism to solve the strong CP problem. So the idea that if you have 2 copies of the standard model, you need an additional ingredient now to solve the strong CP, which is breaking the 2 QCD group, the 2 SU3 group to QCD. Now, in order to properly study the phenomenology of these models, you need to stick with some specific UV completion. In our work, we studied 2 possibilities: Higgsing the 2 SU3 or dynamically breaking the 2 SU3 with some fermion condensate. And let's just have a look at the simplest case here. So first of all, the beauty, I think one of the beauty of this kind of construction is that parity is actually fixing all your parameters in the mirror work to be the same as in the standard model, at least in the UV. So in principle, you have only 2 free parameters for this model. You have the scale at which you break parity, this B prime, and the scale at which you break the 2 SU3 gauge groups to the diagonal. Now, you are forced to take the scale of parity breaking to be the highest scale of this model. The reason is that you want to make all these extra fields heavy to escape direct bounds from collider searches and cosmological constraints. Again?
Which kind of field?
For instance, all the mirror quarks. You want to make them heavy, otherwise you would have seen them at collider. And to make them heavy, you have to make the electron heavy. The electron would have exactly the same UKAO as the standard model electron. That's why G prime has to be at least 10 to the 10 GeV.
But why does it imply that B prime is larger than B3?
This does not imply it. I'm just saying, that's what I'm saying. B3 is completely free. It's a free scale.
Because I thought you said that.
Sorry. Yeah, B prime has to be very large. B3 can be whatever you want in principle. Yes. Now, making it larger than B prime, making it very large, it's somehow boring in the sense that you are recovering your EFT, just the model that I described before, where you just copy SU2 and U1. You only have 1 SU3, which is QCD, because breaking scale into SU3 group is very large here. While the second scenario, where B3 is low and is possibly accessible by experiments, is the most interesting one. And the reason is just that it gives you a richer and at least a novel somehow phenomenology to look for. So if you take B3 large, as I was saying, you get the theta bar QCD set to 0 in the UV. These heavy gluons are integrated out, and you are left with an effective left-right symmetric model. If B3 is small, now this means that you are effectively setting theta bar QCD 0 only at a low scale, where QCD is obtained as from the breaking of the 2 SU3 group. The running of the 2 theta angles are different because below parity breaking, you have different masses for all your constituents, and so they run differently. And you get a phenomenology that can be looked at colliding. Probably I don't have much time to discuss all of these, but in the simplest case where you Higgs the 2 SU3 with the bifundamental scalar, you don't care at the moment about the additional hierarchy problem that you may have. Then you end up with a lot of interesting impossible observations. For instance, we expect to have heavy gluons whose mass is set by this breaking scale. We expect to have some heavy scalars, some of which are also charged under QCD. We expect to have mirror quarks, and that now below V3, when QCD confines, these guys form bound states with the standard model quarks, and bound states are fractionally charged, so can be easily detected at collider. And all of this just to say that this rich phenomenology actually constrains quite a bit your model. For instance, at the beginning I said you have 2 free parameters in this theory, V prime and V3. And here you can see how the parameter space looks like. You have a lower bound on V prime from direct searches of heavy quarks, these fractionally charged bound states at colliders. Then you have bounds from heavy gluons, and the upper bounds come from requiring that SU3 prime does not confine, otherwise you wouldn't break to QCD. And the limits imposed by this higher dimensional operator. You see how, in principle, from a very large possible parameter space, we are constraining V prime to live in 4 order of magnitude also, which in my opinion looks really, really interesting.
Sorry, one quick question. So V prime is the wave of the
Of the
right-handed
Higgs.
Higgs.
Yes.
The right-handed Higgs.
So say again?
The right-handed Higgs.
Yes. But,
And
so here it doesn't make much sense of calling right-handed Higgs, right? Because it's the Higgs of the
Sure,
other
sure.
set of
yeah, HR. I mean.
Yes, yes.
But then for the quark masses, like the mirror quark masses,
Mhm.
they get contributions both from V prime and V3, or like try to understand.
Okay, 3 level just from V prime, right? Because it's just the Yukawa times V prime.
But then yeah, maybe I got confused. I think you said at some point they can be much lighter, but then V prime is pretty large.
Right, but the Yukawa is pretty small.
So you just mean like the okay? So
I mean, just
some-
understand what the up Yukawa and the electron Yukawa are pretty small, no? 10 to the minus 5 or so.
yeah, but like I think if I'm at V prime of like 10 to the okay, I guess you're
So I
talking
think-
about the lower range. Okay.
Yeah, that's what I meant. So if you take 10 to the 8, you will get a TVU prime, which is excluded by collider searches.
Mhm. And what do you do with the mirror neutrinos and the mirror photon?
So okay, yeah, good question. Yes. So the mirror neutrinos, in principle, you have exactly the same problem as in the standard model, in the sense that you in this minimal setup, you cannot explain neutrino masses. You need to add additional stuff. Okay, so you can think it's some dimension 5 operator, a la Weinberg, as for the standard, as in like in the standard model and in the mirror work. For the mirror photon, so here is armless, in the sense that this mirror photon coupled just to mirror stuff, doesn't see standard model things, so you cannot easily detect it. You may, so the problem that you may have is with the kinetic mixing between the two photons, the photon and the mirror photon. But I have a backup slide if you want. We can come
Sure,
back at the
we
very
can talk
end.
later. Yeah.
It's a bit technical. The reason why in this kind of model, so the kinetic mixing at level you can easily avoid it. For instance, embedding this U1 in a larger group. That's why the SU5 I mentioned before. If you embed the U1 in the SU5, you cannot write anymore any kinetic term between those. Okay, at 3 level. Then you have loop corrections. The first loop correction, the first relevant one comes at 4 loops and is mediated by gluons, as I will show you. I can show you at the very end.
Sure.
And this kind of class of model is very suppressed if you break QCD, if you break the 2SU3 group very low, because you cannot connect. Yes.
Yeah, sorry, I have also a question regarding the mirror photon. So if you reheat at the same, if you reheat both sectors during the reheating, then you will have the non-negligible delta effective contribution from the mirror neutron to mirror photon.
From what side?
You have the delta ineffective contribution
Yes.
from the mirror photon, and then
Yes.
I think then it will be constrained.
That's correct. In fact, if you start studying the cosmology of this model, we did in a following paper, you find that you need to require T-rating to be not very low, but low compared to the scale of your masses. So with V prime, yes, that's right.
Yeah, I had more or less the same question. It's a low compared to V prime or low compared to the electron in the other sector?
So yes, low compared to. Okay, the point will be is that you don't want to have your dark photons into equilibrium. Okay, these dark photons will be are produced by diagram of this sort. Sorry, can I draw? So you have, imagine a loop diagram where you have, so you have 2 gluons, then a loop of heavy quarks, the 2 photons in the external legs, okay? So here we'll have a proportional by the, here you will get a proportionality to the mass of the heavy guys and therefore to V prime. And what you find is that you need a reading temperature which is low compared to V prime and not the mass of this gas. I can show you later, but
So
yes.
are you assuming that the reheating there is a bias towards the standard model things, or you're not reheating the electrons to the dark sector? Are you?
So these electrons are just coupled to the mirror photons, not to the standard model, right?
Right, and the reheating comes from.
Because I
something
mean,
that's only the inflaton only reheats the standard model sector then.
Yes, you have to assume that if the inflaton goes directly into the mirror photons, then you have problems. Yes, absolutely.
Yes. So
Yes.
isn't that breaking your C2 symmetry, and does not lead to any problem?
Imagine that the inflaton just couples to the X's, not to the photons. there it will couple easily to the lighter guys that the heavy, like it would decay into the lighter guy more than the heavy guy. And so I agree with you, in principle, yes, you have to come up with some models that does this, but not in general. Okay. But still you have to require a low T rating if you want to be phenomenologically viable from point of view of cosmological constraints. Okay, good. So, like, I'm aware there are many details that I'm just skipping here, but I'm very happy to discuss with you further. But I would like to move to some work that is still a little bit in progress, but I'm very excited about, and concern now CP solutions. So, CP solutions in general are somewhat different than parity solutions, and the main reason is the following. So even assuming CP is an exact symmetry of nature, again, we can repeat the same argument. GG dual is sent to GG dual is sent to minus GG dual, and therefore theta, the Bayer theta angle, has to be 0. However, now also our Yukawas have to be real, and this is problematic in the sense that we are safe from a strong CP problem point of view, but then we don't know how to recover the CKM phase. So usually this kind of solution need a more complicated kind of construction to recover the standard model at low energies. Probably the only solution based on CP that is well known is the Nelson bar mechanism. So I want to give just very few details just to compare with the following solution that I'm going to present. The idea here is that we want to find a way to have some complex phase in the quark mass matrix, but at the same time we want to have the determinant to be real. So how do people do this? In general, you can add some vector-like quark cube, some scalar eta, assume that the CP is spontaneously broken by the bed of the scalar in such a way that you get a quark mass matrix that look like this. You have a lower right component, which is the standard model quark mass matrix with Yukawa's real. You have a upper left component, which is just the mass of this vector-like guys, also real because of CP. And the only phase comes here, the 1-2 component of the mass matrix, in such a way that the determinant is clearly real because the complex phase is multiplied by 0. And you still have a phase such that if you diagonalize this mass matrix, you find that your CKM matrix has a complex phase. However, you may argue, depending on your taste, that this looks minimal, but there are many problems. First of all, you find that you need more than one scalar to get the proper CKM phase. You find that you have somehow to constrain the coupling of these additional scalars, because otherwise they can put some phases in this component here, and to do so you have to add some additional symmetry. Then you find that to correctly get the CKM matrix, you need to require this component to be much smaller than this. However, this component gets corrections to higher dimensional operators, which in principle are large. So you need to add a lot of ingredients, some Zien symmetry to suppress this operator. In addition, there are radiative corrections that you have to get under control. So the decision becomes very soon very complicated and depart from the minimality that you may have wondered. So we have been thinking a little bit around this idea of solving the structural problem with CP, and we were trying to understand: is it really necessary to add vector-like fermions and complicated fermion spectrum to get a real determinant for the quark mass matrix, but still a complex phase for the CKM matrix? And the answer is no. We found that in principle, even just within the standard model fermion sector, you may find some appropriate pattern of Yukawas that have this property. For instance, let's imagine to take now the upper Yukawa to be lower triangular, and the down Yukawa to be upper triangular, so that if you compute our depth of yu yd, you just get the argument of the product of the diagonal entries. Okay, so bear me with a second, and then I'll show you how to get this. Now, also imagine that you just have one scalar in this theory, and this scalar has the same charges as the standard model Higgs, and CP is only broken softly by the web of this scalar. So the web of this scalar is the only quantity that is complex in this theory. You write down your Lagrangian, which is exactly the same as in the standard model, and you immediately notice that now you get equal and opposite phases in the up and down Yukawas, such that the strong CP problem is solved. Because if you take the product of any yu, yd, this quantity is real because the phases cancel between the two. And there is also some hope for the CKM matrix because both yu and yd may be complex. And being complex, once you make them diagonal to get the CKM matrix, they will still have a phase. Now, let's do things more carefully. First of all, only one X in the theory is not enough. You can always rotate this vector to be real by an appropriate hypercharge rotation. So you need more than one scalar. You need the flavor symmetry if you want to get that pattern of Yukawa. And in addition, we only want to softly break CP, maybe only in the scalar potential, in order to get under control all radiative corrections to TP. So after thinking a little bit about this, we came to the conclusion that the most minimal setup, in our opinion, is some sort of 3x doublet model equipped with some flavor symmetry that in the most minimal case is just a U1 flavor symmetry. In fact, let's take these charges now. They're very simple charges under the flavor symmetry. The scalars are charged, all Fermis are charged, and you get now that only these Yukawas are allowed. The first scalar, H1, couples to the diagonal terms, H2 to the top diagonal, H3 to the remaining one. Now, let's look at the scalar sector. We just have some quadratic and quartic interaction. We want to spontaneously break CP and the U1 flavor symmetry. So we only break it in the relevant operator HH dagger, which means that the off-diagonal mu ij are complex. So we have three phases in the theory. I'm calling B12, B23, sorry, beta12, beta23, and beta13. Then you want to rotate from the interaction basis to the mass basis with some unitary matrix U. And let me work in the small mixing approximation in order to do everything analytical. This is the form of the U matrix that you get. So you get some, you have in some three angles, which are the ratio of the off-diagonal terms over the diagonal ones, and three phases. And now, for this model to be phenomenologically viable, only one X can have dev, and the other two X have to be very heavy. Since we don't want to worsen at least the standard model hierarchy problem, we can take 2x to be very heavy, even at the Planck scale, and developing which means developing a very large and positive mass term, while the standard model X, which from now on will be H1, gets a small and negative mass square term, develops a web, and leads to the usual electroweak breaking. So now, with these conversions, we can look at the Yukawas. And the Yukawa interaction becomes something just like this, where all these Yukawa parameters are now multiplied by some element of the rotation matrix, right? In particular, now you can check the Yukawa interaction with H1, which is the X, which is the only guy that gets a web, so that gives the only contribution to the quark mass matrix. And you see that all the diagonal entries now are multiplied by the same quantity, U11, U11, U11. Here it will be U1, U dagger 11. For the D quark will be U11. And when you take the argument of the determinant, this phase completely cancels. Or if you want, in the small mixing approximation, we can rotate the phase out of the diagonal elements. So when you take the determinant, this is completely real. Then you can diagonalize the quark mass matrix, and you find constraints from CKM measurements, and you find that all of these are proportional to some Yukawa parameter times an off-diagonal entry of the matrix that rotates the scalars to the mass basis, and the just log invariant is proportional to some combination of these two phases. So we need to check now that the solution to the Strong-Field problem is of a very good quality, in the sense that it does not get spoiled by radiative corrections. Radiative correction would come from corrections to the Yukawa mass matrix, so you have to compute at one loop these diagrams. Now I will skip all the details, which are not extremely important. The only point here is just that we are softly breaking CP and the U1 flavor in the scalar potential, which means that this cannot give any large log in the RG flow of a dimension 4 operator like a Yukawa interaction. So the only things we expect is that threshold corrections that, if you want, in an effective field theory picture, comes from when you integrate out the heavy guys. And in fact, we find that the only term which can give you a complex phase is proportional to log of m2 squared over m3 squared. So we can compute this, and clearly the most dangerous contribution comes from the correction to the up 1-1 Yukawa. The reason being that when you compute the determinant, this gets enhanced by 1 over the upward Yukawa, and we found the constraints on the off-diagonal, on some of the off-diagonal entries of the matrix U, and now I'm parameterizing in this way, times these free parameters that are free as in the standard model. So these the Yukawa parameters. And then you may be worried about higher dimensional operators. Now, the beauty, I think one of the beauty of this model is the fact that the only guy that, the only scalar that gets above is the standard model X. So, at tree level, the only correction you get.
Sorry, just a clarifying question.
Yes.
When you say standard model Higgs, that's capital H1? So
yes.
The mass eigenstate?
Yes.
So all three of the little h's get their events, right?
That's right, that's right. Okay. But they will all be proportional to V, like the standard model X times some cosine or sine, yes. So they will all be order V. That's what I mean.
Okay, and such an arrangement is not tuned?
It's tuned in the sense, such an arrangement.
So if you go back to your original Lagrangian, so the tree level.
Yes. This one for the scalars.
Yeah. So you have a mixed mass term and a mixed quartic in general, right?
Yes.
So.
Yeah, it's tuned in the sense of the standard electroweak problem. If you make the two guys very heavy,
not any worse.
You still are requiring one to be very low, though it gets correction from the other guys. Yes. Yeah, we are not solving the electroweak hierarchy problem. Agree. Yeah, but that's the only tuning. The other two guys can be taken to be M-Planck. While I will get there later, but the off-diagonal entries are technically natural, in the sense that taking them to 0, you restore CP and U1 flavor. So they are naturally small. Okay. So exactly. So now you have to rotate this to the mass basis. Each of these get a VEV, and the point is that since the only VEV is the electroweak VEV, the tree-level correction here is proportional to V squared, where V is 175 GeV, over lambda squared. So this correction, unless you take lambda very small, is completely negligible for theta. But they may be dangerous if you close the loop. Because if you close the loop and now you compute this loop is proportional to the mass squared of the guy that is going through the loop. And if one of these heavy guys is going through the loop, you get something that goes as M2, M3 squared. So you can compute this the corrections. I will trust me that this is the most dangerous one, but you can check it computing all possible contributions to the determinant, and you find another constraint on the off-diagonal entry of this matrix that rotates the scalar sector times the ratio between the mass of the heavy scalars over this scalar lambda, this scale lambda, times again a free parameter, which is the Wilson coefficient of this operation.
And the betas were the exponent in the exponentials.
Sorry, say again?
The betas, beta 1, 2, and 2.
Beta.
Were the exponent.
Yes, they are in the exponent.
The,
and you
the
take,
exponent of the. Yeah.
yes, exactly. They are in the exponent of the off-diagonal entries of the U matrix. Yes. Okay, so you get also this constraint here. So now I'm entering into the work in progress. First of all, we want to estimate these parameters, understanding the theory has to be tuned or not. To do so, as I showed you, you have actually some free parameter. You don't know what this Wilson coefficient is, and you don't know what these Yukawa parameters are, because actually what is constrained is only these contributions. As you can see at first order, CKM is given just by the D quark matrix. The reason is clearly because if you look at this matrix, this at first order rotates only the left-handed fields. Okay, and so therefore there are these three parameters that in principle you don't know what they are, and you don't know what is a natural value for them. So what we are doing at the moment is trying to come up with some reasonable flavor assumption that give you a natural expectation for all these parameters. There are works done by Weinberg, Hall, and Georgi, where they try to they add so they try to explain the smallness of the Yukawas as breaking parameters of some U1 symmetry, one for each quark. So if you do this, at the moment we come up with this result for the epsilons. And remember that the epsilons are the ratio between the off-diagonal and the diagonal entries of the scalar matrix, which are squared. Sorry, these are masses squared, of course. These are m12 squared over m22 squared, for instance. And I would argue that these are not that small. And again, as I told you before, these are technically natural. So the theory doesn't look that tuned. And then you can start asking very interesting questions. For instance, so far we have been adding a soft breaking. We have been soft breaking CP and the U1 flavor. And soft breaking again means just that we don't know, the origin of this break, right? And we can try to actually spontaneously break both CP and the flavor symmetry. Imagine, for instance, that now you have some scalar that gets with such a potential that gets a complex band. This will and also has some flavor charge. This would automatically spontaneously break both the U1 flavor and CP. In addition, spontaneously breaking the U1 flavor, we end up with a Goldstone. And this Goldstone will have some now flavor coupling that can be looked at collider. For instance, this may give some k into pi Goldstone, which sets a lower bound on the decay constant of this Goldstone, order 10 to the 10 GeV. And you see that we may start also restricting the allowed window for the BEV of the guy that breaks the U1 flavor. In addition, if you care about quantum gravity breaking global symmetries, you may think about gauging the flavor group. And once you start gauging the flavor group, you end up with a Z prime now, if you spontaneously break. And this will give you other flavor constraints. In any case, this is all work in progress and a question that we are trying to answer at the moment. While the message that I would like to pass you here is, I'm really excited by this solution because, first of all, I believe this is the simplest solution to the strong CP problem based on a CP symmetry. We just need a Higgs doublet model here and an appropriate flavor symmetry. Somehow it looks like we are rephrasing the strong CP problem in terms of parameters of the scalar potential. The smallness of the corrections to the theta bar have to come in this model from the parameters of this U matrix that rotates the scalar sector. And this may lead to interesting avenue if you try to connect it with the electroweak hierarchy problem, the size of these parameters. In addition, it is very important in this model the flavor symmetry that we are introducing. And this may lead to connection to the flavor puzzle. I started from Yukawa that have these patterns, just because it is easy to see that here only the diagonal terms are will contribute to the argument of the determinant of yu, yd. However, you may end up with other patterns defined by appropriate charges for your flavor under your flavor symmetry, which may explain at the same time the hierarchies between the quark masses. For instance, imagine you have 3 X's, one that each, like the first one coupling only to the first column, the second one to the second column, and the third one with the third column. Now, the smallness of the parameters that rotate these X's to the mass basis may also explain why this entry is much larger than this is much larger than this, at the same time for the up and down quarks. So it seems like also studying this in connection with the flavor puzzle is a promising avenue. So to conclude, I think that to get a better understanding of the strong CP problem, we should try to understand its landscape of solutions. And in this sense, P and CP solutions offer remarkable framework. Here I presented 2 new mechanisms that we studied recently. One based on parity solutions, where you are fully copying the strong CP problem. You are fully copying the standard model, and you are adding a breaking pattern of the 2SU3 that leads to a zero theta bar. And the second one based on CP with a simple flavor symmetry and 2 additional Higgs doublets. Hinting to very, very interesting, in my opinion, connection with other relevant puzzles of particle physics. Thank you for your attention.
Any questions for Claudio?
Yeah, so could you go to the slides of the quantum correction on the power? Yeah, because I just confused why.
Which one?
The log terms, the slides with log terms. So I just very naive question is why do you neglect other log terms?
Yeah, so we don't neglect. So this log term, so okay. First of all, since the only CP violating parameter is a soft breaking in the scalar potential, we cannot get any RG flow in the 4-dimensional, like imaginary contribute, like RG flow is proportional to the CP breaking for a dimension 4 operator. Okay, so here it's not very easy to see, but so the guy H1 is the standard model X. So this is the standard model running. Okay, and this is this must be real. No, you cannot see it from I can show you the calculation, but because of the unitarity of this U matrix, you find that this contribution is also just a standard model contribution. So doesn't know anything about this CP breaking. So also cannot induce any CP breaking. So this term just shifts the real component of the Yukawas. Okay, not exactly as in the standard model, because clearly now we have more objects, but we know that the standard models are very small because are also proportional to the product of 3, like each Yukawa receives an RG proportional to 3 Yukawas, right? So it's much smaller. Therefore, these don't contribute. It's not that we are neglecting that. This guy is just a real contribution. And again, because of unitarity, once you sum over contribution from H1, H2, H3, you find that this guy is real. So the only guy that is complex is this. So this is the only contribution to the only complex contribution to the Yukawas.
Yeah, any questions?
I have a kind of broad question. So cosmology-wise, would you say like these like CP-based solutions, they are safer compared to the P-based solutions, or there are similar issues that you might address?
So I didn't think much about the cosmology of these CP solutions, but in this simple model where you are only adding two heavy Higgs, I don't see anything that can be dangerous from a cosmological point of view, no? What do you do?
With all the fermions, even in the P problem.
No, in the CP.
And
in the
the
CP.
CP.
No, in the P, yes. In the P, there are several problems given the fact that you are doubling the full standard model spectrum. So, but in the CP ones, in particular in this one, I don't see any. The others you may worry about the vector-like fermions, but I guess you can make them heavy. Not too heavy because. Not too heavy because, as I told you, to recover the full CKM, you need this quantity to be much smaller than this. So you cannot make these vector-like fermions arbitrarily heavy, and you may end up with problem cosmology, but not with the solution that I presented today. This solution is very safe from cosmology, I think. Oh, and by the way, sorry, I forgot, but I should say the solution that I presented today was actually partially studied by Glashow, so long time ago, now 25 years ago. The only problem is that in the way he formulated it, he had three Higgses with the same mass and the same valves. This was pre-LHC, so at that time it was possible. Now we know that this is clearly not possible, and therefore that's why we need to make two of these Higgses very heavy, and this leads to a different phenomenology, in particular in terms of the higher order corrections.
So this is like a generalization of the other model, no? So in V3 going to infinity, let's say, you recover the one with a single SU3.
That's right. Yes,
It can be thought of as
absolutely. That's it. Yes, it's exactly like that for the P solution. Yes.
Sorry, so you mean here you have three flavor of Higgs, then two of them are very heavy, and
that's right.
And then can we just also set the naturally bound, on its fixing, given the polygon?
So not on the diagonal entries of the matrix, yes, and that's why I said the electroweak clarity problem is there.
Yeah.
At least in this very simple.
What I mean is, can we just transfer this as a constraint?
And not on the off diagonal, no, because the off diagonal ones are CP, are the only CP breaking. Okay, so the off diagonal entries are CP violating. So they only receive corrections proportional to themselves. They cannot receive correction proportional to the diagonal elements, clearly, right? And so that's why they are technically natural. That's what I was saying before. No, they don't get large corrections. The diagonal ones, on the other hand, yes, they reintroduce one the other, and then you would expect all of them to be comparable. But we need to take one very small to describe the standard model Higgs. Right?
So the quartic is also diagonal, right? Or no?
This is not important because this would give you higher order correction again to the diagonal ones, not to the off diagonal. So no, can be not diagonal, but still respect the U1 flavor symmetry. So you cannot have all possible combinations.
Right. Okay. Yeah. That sounds.
Yeah. It's not U1 breaking because otherwise it wouldn't be soft breaking because we would be breaking some coefficient with some coefficient of a dimension 4. Right? No, we need to take it. We need to have only soft breaking if we want to get the radiative correction under control, don't get large logs. And therefore only these guys have to DCP and U1 violating.
One question, at the end you said about potentially gauging this flavor U1 symmetry, right?
Yes.
And then you said something about you have to make it heavy enough so you don't have collider bounds with this extra Z prime, right?
Mm-hmm. Yes.
Is there any issue with taking it just arbitrarily heavy, or does that affect the quantum corrections to theta? Like you had some terms that were like M3 squared over lambda squared.
Yeah.
Is like if you make M3 is and the mass of the Z prime are correlated, so you would.
So yes.
Potentially.
Right. Yes. You cannot take it as large as you want in the sense that if you want, so if your V completion is a gauged U1 flavor symmetry, and then you spontaneously break it, then the breaking of CP and therefore these off-diagonal elements are proportional to the mass, to the value of this scalar that is breaking the U1. And so because of the constraint I showed you before, it cannot be very large. Right? So you have an upper bound from this, and in addition, you may just write a dimension 4 operator, dimension 6 operator. Imagine this. A dimension 6 operator, not some. That introduces theta bar.
Right,
And
so you
you
have a
don't
quality problem again.
Exactly, you may start having quality problems such that this valve cannot be large. And so you have an upper bound from this, a lower bound possibly from collider searches, or more than collider searches, this would be like B mixing, kaon mixing, so indirect searches of this. And this would restrict the window of parameter space for this solution, yes.
Any last questions, Claudio? All right, not. Thank you again.